Hi students, today we will discuss about the force acting between the two infinite length conductors carrying current. So suppose let us consider here are two conductors which are carrying current. Suppose this is your AB, this is your CD. The length of the conductor, let this is infinity, right? So now we have to find out the force between these two parallel conductors carrying current. So as we know, suppose the current passing through this is your I1 and the current passing through this is suppose I2. So as we are knowing, if the current is passing through this AB conductor, then on the conductor CD, suppose this point we are considering, so here there will be a magnetic field. So we know what is the magnetic field produced by the current carrying conductor, that we already know. This is your perpendicular to the conductor CD. So here the magnetic field produced due to the current flowing through the AB will be in this direction. Suppose this is your B1. So again, if a current carrying conductor is placed in a magnetic field, then it will experience a force. So in this case, what will be the direction of the force? The direction will be perpendicular to the conductor CD, and this will be here towards the AB as per the Fleming's left hand rule. So here this will be the force acting on the current carrying conductor, that is CD. Similarly, if we consider the magnetic field produced by the conductor CD, then this will come as, we can see here. So the force in this case, this is your inward, and in this case the force will be, that is in this direction. So suppose this force is your F1. So now here this force F1, we find out the direction by using Fleming's left hand rule. You know what is Fleming's left hand rule? Suppose we are stretching our thumb, that is first finger, and the central finger, so that they are mutually perpendicular to each other. Then if the direction of the magnetic field is given by the first finger and the current direction is given by the central finger, then the direction of the force will be given by your thumb, right? So we'll apply this Fleming's left hand rule to find out the direction of the force acting on a current carrying conductor when placed in a magnetic field. So in the similar manner, we can get the direction of the forces acting on the parallel conductors carrying current, right? So in this case, the magnetic field is in this direction. So I think now the directions are clear to you. So now we can find out the force. So how to find out the force actually? Force is equal to, you know, that is your ILV sin theta. So here you can see this will be that F2, that is the force acting on the current carrying conductor, that is CD. So F2 will be equal to your, that is I2L, that is the suppose length of the conductor, then this will be your B1 and sin theta. So sin theta is known as the angle between the magnetic field and the current carrying, that is direction of the current. So here that is 90 degree. So this will be your I2L B1. So again you are knowing in this case that force will be equal to your I2L, and the magnetic field which is produced by a current carrying conductor at a certain point, that we are already knowing the magnetic field B is equal to mu naught I upon 2 pi r. Here r is the distance between the conductors, right? So here the magnetic field which is produced due to the current I1, so this will be your mu naught I1. So I will write here I2L. For B1 I will write mu 2 I1 upon 2 pi r. So what I get here? Your F2 will be equal to your mu 2 upon 2 pi. Here this will be I1, I2, then r, and this will be your L, right? So this is the derivation for the force acting on a conductor carrying current if it is placed near to another current carrying conductor, right? So similarly, we can find out the value of F1 also, that is the force acting on the first conductor, that is your AB. So here this will be equal to your AB, so your F1 will be equal to your similar manner, this will be mu naught upon 2 pi I1 I2 upon r, and this will be the length, right? So as you see from the diagram, the forces acting between the parallel conductors carrying current, they will be in opposite direction. So we can say vectorically that F1 is equal to F2. So here we can see here F1 is equal to F2, only the direction is changing. So I can write here this is F1 equals to minus F2, right? So I think it is clear to you. So if we want to find out the force acting per unit length, so what it will come? It will come here F2 is equal to, you can see here F2 will be equal to here, that is per unit length. So F2 upon L will be equal to your mu naught upon 2 pi, this will be I1 I2 upon r. So this is an important derivation in concern with your coming CBSE board exam 25. So I think these concepts you have to understand and you have to derive the derivation. And again, you have to remember, if two forces are, that is two conductors are carrying current in the same direction, then that is known as parallel currents, and the nature of the force will be attractive. And if the conductors are carrying the currents in opposite direction, then that is known as your anti-parallel currents, and the nature of the force will be repulsive, right? So what we get, if that is for parallel currents, the nature of the force will be attractive, that is attractive, right? Similarly, for anti-parallel currents, we will have, that is, suppose if I1 is parallel to I2, we can write here, if your I1 parallel to I2, then this will be equal to attractive. And if I1 is anti-parallel, that is the angle between them will be, they are anti-parallel, then the nature of the force will be here repulsive, right? So these are the important conclusions regarding the force acting between two parallel conductors carrying current. Here another thing is there is a important definition in the exams. It is asked, define 1 ampere of current. Define 1 ampere of current. So how you can define this? See here, suppose we are assuming this one, suppose we are assuming your R is equal to 1 meter and your I1 equals to I2 equals to suppose 1 ampere, then what will be the value of F? Your force will be equal to, you know, mu naught value is 4 pi into 10 to the power minus 7 upon your 2 pi. So this will be equal to 2 into 10 to the power minus 7 Newton per meter. So right. So here you can define current of 1 ampere. So what is the current of 1 ampere? Here you can see the definition will be, you can write that 1 ampere of current is defined as that steady current which is flowing in two parallel conductors carrying equal currents of negligible cross-sectional area, and if placed in air at a distance of 1 meter apart, then the force between them existing is 2 into 10 to the power minus 7 Newton per unit length of the conductor, right? So this is a important derivation and important definition of your 1 ampere. So I think you all understood. So you can derive if it is asked in your exam. So important thing, we can do the conclusion here that two parallel conductors in current, the force between them will be attractive if the currents are in the same direction, that is parallel currents. If the currents are flowing in opposite direction, then the nature of the force will be repulsive, and the force acting on each current carrying conductor per unit length is equal to mu naught upon 2 pi, that is, you can see mu naught by 2 pi I1 I2 upon R, right? I think it is clear to you. Thank you.